Assalamu alaikum. Assalamu alaikum, guys. In our last class, we have discussed or we have derived maximum signal to noise power ratio, right? At hot condition, right? We have derived this one. So in this lecture, we will find what is the expression of the probability of error. So this lecture is the probability of error or error probability. So why you are finding it? Now, signal to noise ratio, signal to noise power ratio uh, was a characterization matrix to or performance matrix actually to find a system how good it is or what is this performance matrix. It's a one kind of performance matrix. Another kind of performance matrix is the probability of error or error probability. So what the probability of error do actually? So when we transmit a signal from transmitter to the receiver, when it receives, it actually tries to calculate how many of the bits that was transmitted was received as a error bit. Okay, means actually it's a performance matrix or quantity that calculates the erroneous in the receiver side. Okay, so the goal is to minimize the probability of error. That's actually, if I know what is the probability of error in a system, then I can minimize it to make the system better, right? The typical value is 10 to the minus 6 to 10 to the minus 8. 10 to the minus 6 actually nothing but this is the typical value. This is a typical value. 10 to the power minus 6 actually nothing but 1 in a million. If you transmit 1 million bit from transmitter, in a receiver 1 bit can be errored or can be received as an error bit. Okay, that's an acceptable. So the bit error rate or probability of error will actually give you the understanding of the robustness of the system, how good it is. Okay, now let's draw. Oh, sorry, I started with a wrong slide. Okay, so what is our schematic diagram for a digital communication system? Let's draw it. I have drawn it again and again and again. By this time, you should have like memorized it almost. So if I transmit an XT signal that in a channel, while in transmission, some noise got added in T, then the output of the channel receiver as a YT must go through an receiver has a impulse response HT, and the output of this HT will be RT signal, which is sampled at T equal to T. So our received signal is RT. Okay. This is the typical schematic diagram of the transmitter to the receiver, the simplest form. We have already in our SNR, you remember in our S7 calculation, we already shown that if we want to receive a maximum signal to noise power ratio, this impulse response of the receiver must be equal or matched to the pulse shaping of this transmitted signal. We already did that calculation, right? Okay, so what is this RT signal? This RT signal is nothing but this. Also, I have written it previously, right? This receive signal is nothing but the signal pass noise. So this is the signal part, minus infinity to infinity, pt minus tau h tau d tau plus n tilde. You see this receive signal n, this one, when it goes through this transmitter, the receiver impulse response, it is changes. So that's why I used a different. This is a noise with the same noise variance. I mean the Gaussian distribution. So this is Gaussian. This is still Gaussian. This was also Gaussian. This was also Gaussian. So this is also a Gaussian in nature. Okay. But I just changed it to a little bit so that to distinguish that this is not the same noise of this one. This noise component is not same as this one, not as this one, because it has to go on through all these processes. Okay. Now in okay, okay, let me write it here again. This signal A0 minus here we are saying that this guy n is Gaussian. Now we already shown that pt has to be equal to the p tau has to be equal to the h tau for the mesh filter. We already have shown you this one. Now for this part, we already have okay, let me rewrite it, what we did for our maximum SNR. What we did that minus infinity to plus infinity, we say that pt has to be this part has to be equal to the this part for matching. Means actually this becomes square. pt minus, just go back to our last slide, the slide of the SNR. So beta plus, so this is our signal. Now this part is nothing but what we write it. Remember in our just previous slide we have written that is nothing but the minus infinity to infinity p square tau d tau, right? Which actually we write it as a ep, like the energy of the pulse shaping filter, right? We denote it as a energy of the pulse shaping filter or the transmitter filter. Pulse. We have discussed this part in our previous slide, right? In the SNR field. So this part I can write as a A0 FEP plus N tilde, right? Okay, this is actually the signal that is received. This is actually the signal that is received after the sampling here. Here after the sampling at this point. Okay. Now we know who is what. We know this guy. This is our transmitted signal or symbol. So this is actually our energy. This is actually this one, energy of the, and this is the Gaussian. It's actually Gaussian noise. We have discussed about this noise detail in our AWGN slides, where I had discussed detail about the nature of this Gaussian and the distribution of this Gaussian. There I have shown you that the expected value of this n tilde is a 0. It's actually 0 mean, eh? So 0 Gaussian having distribution 0 mean, and expected value of this variance, n tilde variance is what? And 0 by 2. We know this noise, we have also seen it in our previous slides. H, this is actually the variance of this noise data, right? And we have solved it already, that n 0 by 2 minus infinity to plus infinity b square from our previous slide. You already know it. So that solution was actually this one, n 0 by 2 and ep. That was our solution in our previous slides. I'm just repeating, you already know this stuff. I'm just for the sake of derivation. Now, what is the nature of this? I have already discussed this in our EWGN slides, so just let's repeat it. The n tilde is what? This is actually a Gaussian. So this is actually the symbol Gaussian having a mean 0 with a variance. What is the variance? This is the variance. 0 by 2 EP. From where I get this equation? This is actually general expression of a Gaussian which have a, we can be a Gaussian distribution have mean value mu and its variance sigma square. From this I have discussed about this detail in our so this is the mean in our AWGN slide. So this is the mean. So Gaussian distribution is expressed by this one. This is the variance. Okay. Okay. So in this scope, let me give you that if this is a 0 mean having unity variance, if a Gaussian distribution have a 0 mean with a unit distribution, we call it a standard Gaussian. We call it a standard Gaussian or standard normal or standard normal. Why I'm talking about this? Because after a few slides we'll actually we will use this definition. That's why I'm giving you this one. Okay, so let me. Okay, so what is our signal RT? Our signal RT is nothing but A0 EP plus n tilde. Okay, that's our receive signal. Now here A0 have two options, right? It can be minus A or it can be plus A. Oh, sorry, plus A. Remember why we are talking about a plus A minus? Because we took the very basic modulation BPSK. Remember at the very beginning of our, from the very beginning of this slide, we are taking as a BPSK. That's why. So remember our transmitted signal, example transmitted signal. This was the series one when we use 0, 1, 1, 0, 1, 0 means actually. So we took 0 is A, 1 is minus A, right? Something like that. 1 is minus A, 0 is A, 1 is minus A, 0 was A, right? Remember this. So actually 0 was expressed by A, our 1 bit was expressed by minus A. This is actually our example we are using since the beginning. So RT can be plus minus A EP plus n tilde, right? So RT has two possibilities, right? RT can be A EP plus N tilde when A0 equal to A, right? Or RT can be minus A EP plus N tilde if A0 is minus A. From our previous example, okay. So RT, remember, RT is actually the output of the sampler. Okay, now here we will discuss little bit about the Gaussian property. About this Gaussian property, we'll discuss about. So in Gaussian noise, if a Gaussian noise, if a noise, so for example, n is a noise. If a noise is Gaussian, having a mean and variance, then okay, let's say this is a Gaussian property. Gaussian property. Let's discuss about some property. So this is some Gaussian property. Okay, then n plus k. If n is a noise, if I add a k is a constant here in our cases. If you add a constant, what will happen? The Gaussian will be what would be your its mean and distribution and in our variance. So for our cases, this is AWG. This our Gaussian is actually our this noise AWGN, additive wide Gaussian noise, which have a zero mean. If a Gaussian noise have a zero mean, if I add a k constant, the mean will be shifted to the that constant plus k. The mean will be, because it's zero, so 0 plus k will be the zero. Sorry, k. But its variance will be the same, because variance is nothing but the distribution of the energy, and it's a constant. Okay, so this variance is unchanged, but this is not unchanged. This part is not unchanged. If so, let me repeat it. A noise which is Gaussian, if I add a constant with it, what would be its mean? The mean will be shifted to that constant, but its variance remains unchanged. Probably you know it from this Gaussian Gaussian properties. Now, if let us visualize it. Let us visualize this. So the Fn, the probability density function of n noise. So let's draw it. Let's draw a, if a probability density function looks like this, having a Gaussian probability density function. So Fn is the Gaussian probability density function, which if it have a mean mu and it has a variance sigma square, then by adding a constant will shift it to the new constant mu plus k, but its variance remains unchanged. That's actually we mean by this one. Got it? Okay. So what will happen to our signal? What will happen to our this signal RT? So the signal RT, so if RT have two RT have this expression, two possibilities, this possibilities or this possibilities. Let me rewrite it. It's two possibility. RT can be plus A EP plus N tilde or minus A EP plus N tilde. This two possibility. Now, if this is the case, then what is Gaussian distribution? The Gaussian is, you see, this was zero mean previously, right? But you added, so this noise, you see, this noise has a Gaussian distribution. By adding it with a constant, will behave like this. So this Gaussian distribution have a zero mean. Now you add a constant, so that is the new mean. Okay, but its variance is the same. Okay, same thing for this guy, right? So its Gaussian distribution will be minus a EP, EP with having the same distribution. Probably we already know that this sigma square, what is its value? N 0 by 2 EP. You already know this is value. Okay, now both of these expression have the same variance but different mean. So it would be look like. So this is the mean for the positive, and this is mean for the negative, right? So it will look like this. It will be okay. It will look like this. For minus EP, for minus AEP, this is the, so this is for the minus EP, the probability density function of this guy, the probability density function of this expression. Okay, so this is for A0 when A0 was minus A. Remember this choice? Okay, but for this one, this is the distribution, the probability density function, which is A EP. For what? When A0 was A. This one looks good. It should be like this, like this. So what is this point? This point, this is the intersection. This is the point of intersection. Intersection is 0 by symmetry. Okay. Still, you see both of these two distribution, this one and this one, because they are only shifted by their different values, digital values. So their mean value changes, but still they have the same distribution. Sorry, they have the same variance, because we know the variance is nothing but the distribution of the power. Okay. So we already know there. So let's rewrite RT. RT. So RT is nothing but plus A EP. For this one, I'm writing this expression, this distribution. EP plus N tilde, which have a distribution, Gaussian distribution, having a mean, this value AEP, and variance. You remember what is the variance? Variance was, what is the variance? Remember here, did I write it anywhere? Variance? Yeah, this is the variance. This one's the variance. So variance is n0 by 2 EP, or this can be minus AEP, which is actually this one, plus n tilde, which have a Gaussian distribution of minus AEP. I mean, this is the mean and the variance of n0 by 2 EP. Here we will use this expression n0 equal to capital N0, just for the sake of simplicity, nothing else. Okay. Okay. So now let me draw this distribution again to further exploit it, to further understanding. Okay. So now we have two distribution. One distribution is, this, where we have the mean value of A minus AEP for A0 equal to minus A, right? And we have another distribution for with a mean A EP, right? And this is for A0 A, the probability density function. Wait a minute. Okay, now this is actually the point of intersection. The symmetry is 0. Okay, so we let us give it name. This is actually our PDF, probability density function of output RT for A equal to, sorry, A0, A0 equal to minus A, and this is the PDF, probability density function of output RT for A0 equal to A, right? So this is actually our RT, this is actually our RT. Now, for the sake of simplicity, I will replace this one. This is replaced by minus A tilde. This will be replaced by plus A tilde. Okay. Let me rewrite the RT equation then. So RT will be 2. The distribution of RT will be, so okay, distribution of RT will be Gaussian, having now new A tilde with a variance sigma square, or it has a distribution new. This is the with new term, A minus tilde, because we just replace them. So I'm just writing the new equation. It's the same thing of the previous one. Okay, this is for what? When A0 is this is A, so the positive one. This is for A0 equal to A, this one, and this is for A0 equal to minus A, this one. Okay, so you see we have two distribution. We have two distribution for A0 equal to A. This is actually the probability density function, and for A0 equal to A, this is actually our probability density function. This is the distribution. Okay, now this gives a clear picture for us. This is 0, means actually this is some kind of reference for us. This is some kind of reference for us. Okay. For okay, let me rewrite these two guy, so that, so this was equal to a tilde, this was equal to minus a tilde. Okay, now this was, what is this distribution? This is 0, eh? This is their intersection. This point is the intersection. From greater, so RT greater than or equal to 0 will give us what? Will give us A0 equal to A. Will give us A0 equal to A. But RT, this is RT scale, eh? RT, so RT less than 0 give us what? Will give us this A0 equal to minus A. So this is actually a decision criteria. So okay, so what is our decision criteria, or we can say decision rule? Okay, so what is our decision rule? Decision rule, or we can say detection algorithm or mechanism, eh? What is that? If RT is greater than 0, will what? RT greater than 0 is this part. This part. RT greater than 0 is this part, which actually gives us decision of this, which will give us decision, which will give us the decision, or the decision of A, right? Which will give us decision of A, this one. But if it's other, so RT less than 0, less than 0 will give us a decision of minus A, right? So this is actually our detection, so to say, algorithm, eh? So if we decide that it's A, means actually it's a information bit. So info bit A was what? A was our 0, eh? Remember A was our remember what we decided? I don't remember anymore. Let's see, A was our, oh, so A, eh? A. Oh, A gives us 0. Minus A gives us 1. Okay. So A gives us 0. The info bit 0. And this is gives us info bit 1. That we decided. You see how we will decide our, now which bit is what, eh? Now what was our discussion so far? We will find the probability of error, but we didn't talk it about so far, eh? Now we will talk it about what is the probability of error, how to find it, eh? So what is the, when the error will occur? So the question is when does the error occur? Can you tell us when the error will occur? We know because we have only 2 bit. If I transmit 0, if it received as a 1, this will be error bit. If I transmit 1, if it received as a 0, the error will occur. So answer, error occur when I transmit 1, I receive another. Okay, for example, in terms of our equation, in terms of our equation RT, so in terms of our equation, if RT greater than 0, okay, we supposed to receive what? We are supposed to receive 1. But if we received 0, you see, this one, a0 equal to minus a, or when rt is less than 0 will give us a0 equal to a. You see, if I go back, when rt is less than or sorry, rt is this rt, this is rt. If rt, this is our 0, this is our 0 point. If rt is greater than or equal to 0, we supposed to receive this guy a0a, a0a. But if we receive a0 minus a, then the error occur. Or rt is less than 0, we supposed to receive a0 equal to minus a. If we don't receive it, we receive a0 equal to a, then the error occur. That's the straightforward understanding, right? Okay, now we will consider, we will assume, okay, consider. So consider the transmission a0 equal to minus a. This is transmitted. If this is a transmitted, then rt will be what? We know minus a ep plus n tilde. We already replaced this a ep by a minus a tilde plus n tilde. This is our transmission characteristics, right? Error occur for this condition. For this transmission condition, the error will occur. Error occur if what? If this minus a ep plus n tilde, error will not occur if it's less than 0, but error occur if it's greater than or equal to 0, right? So we can rewrite it as n tilde greater than equal to minus will be plus aep. So we know we actually change it by minus it was minus a tilde, but we change it to plus a tilde, right? Because it changed side. So this is the condition. If this is the condition, then the error will occur, right? Okay, so what is the probability of error? What is the probability of error? Now the probability of error for which condition? For we are considering this condition, this condition. The probability of error will occur. Probability of error is the probability that n tilde is greater than a tilde. This one. This is the probability, right? The probability of error is the probability of this one, because this is the erroneous probability. This is the error. This is the error occur. So if this is the probability, then this is the error probability. Okay. Now, probability of error, this can be expressed as a probability density function of this n, So what is the probability density function of this n? It is nothing but, remember what is that? We discussed this probability density function of Gaussian distribution with the zero mean is nothing but this expression. Go back to the AWGN slide, you will find it. So 2 pi sigma square, here sigma is the variance, e to the power minus n tilde n square divided by 2 sigma square. This is actually a well known fact. We already derived this one. So I will not show you the detailed derivation. Go back to the AWGN slide. Where do you find it? So the probability of error, that n tilde is greater than a is nothing but the probability density function of this n. So I can write a tilde to infinity, the probability density function of this one, fn n tilde dn tilde. So this is a expression of probability of, so we can say probability of error is the expression. Okay, so we will detail derive it again. Okay, so probability of error. Now let us assume n tilde, this one, from here we have n tilde by this equation. We assume that n tilde by sigma is n prime, for example. Just I'm trying to simplify it. So dn tilde will be sigma dn prime. If this is the conversion, then we can write probability of error will be a tilde by infinity 1 by 2. I'm doing nothing but the replacing this fn function by this equation, by this one. Okay, by sigma square, just replacing this n tilde by twice sigma square dn tilde. I'm writing it now. I will replace it. Okay, so it will be now is tilde by sigma by infinity 1 by 2 pi sigma square e to the power minus, you see we have this conversion. So n tilde by is n prime, so e to the power n prime square by 2, and then this one sigma dn prime. So this sigma and this sigma, this can be crossed, right? Okay. Okay, now we will have a, in between we will have a definition to make it simplified. So remember this expression 1 by twice pi, this expression up to this, this expression. Remember, we just a few slides back we find probability density function of standard Gaussian with mean is mu 0 and variance sigma square equal to 1. You see, sigma square is 1 here. That's why it becomes a standard Gaussian. For this standard Gaussian, we have a formula that q is the q of u. We know this function, and this is a well-known function. This is minus this u to infinity 1 by twice pi e to the power minus t square by 2 dt. This is called Gaussian Q function. This is actually Gaussian Q function, which denotes which d d which denotes so d denotes the probability that the standard Gaussian random variable is greater than u. Is greater than u. Is greater than u. So we know the Gaussian Q function. Okay. So we know the Gaussian Q function. For this Gaussian Q function, you see the Gaussian Q function is this. This. So we can rewrite this as a terms of Gaussian Q function, where this Q will be a function of this one. Q will be a function of a tilde by sigma. You know, this Q function starts from the this is a function of u, so that will be the function. This is a Q function. Okay, this is the probability of error. Now what I'll do, I will do the replacing of this or substituting these values and these values. What will happen if I substitute this value q? Remember a prime, a tilde was a ep, right? AEP. And sigma was, remember, sigma was sigma was n0 by 2 EP. Yeah, this one. I'm trying to write it in this way. Okay. Yeah. So this is the our if we are like substitute the replacing these values, their corresponding values. So we can actually just rewrite it. Is a Q function. Little bit different, writing it different. So a square EP n0 by 2. This one. So this is actually our probability of error with Q function. So you see, this probability of error was considered for which case? Remember, for this case. Considering this case. If we all do that a0 equal to a, this will be the same probability because they are equal probability. We already seen it in our previous example. They are equal probability. This this is not equal, so they can be interchangeable. This, if I transmit 0, what will be the probability that 1 is received? If I transmit 1, what is the probability that 0 is received? Okay. So for our case, this is actually the this is the probability of error, where we have the this is actually the probability of error, where we have the Gaussian Q function in terms of its Gaussian Q function. Okay, so probability of error in terms of Gaussian Q function. This is actually the very fundamental. Now same equation can be re-derived for different constellation. For example, QPSK, ASK, FSK, all this stuff. So we will actually end here. Assalamu alaikum.